right, everyone, we finally made it. 9.4, part 6, the last part. And we have my favorite test, the ratio test, and then the root test. So the ratio test says let the sum from n equals 1 to infinity of a sub n be a series of non-zero terms. It says that the series is going to converge if the limit as n approaches infinity of a sub n plus 1 over a sub n is less than 1. The absolute value, I should have added that in, of a sub n plus 1 over a sub n. And then it's going to diverge if that limit is greater than 1. If you do get a limit of 1, the test is inconclusive, and you're going to have to use another test. So series involving expressions that grow very rapidly, such as factorials and exponentials, work really well with the ratio test. And you could also use a ratio test if you have an alternating series, because those absolute values are going to take care of that alternation. And so you may just bypass the alternating series test and go straight to ratio test, potentially in some situations. So let's take a look at some examples. You'll notice in these examples, you see factorials in several of these examples, and you have some exponentials, and you'll see why the ratio test is great for these. Okay, so what you're going to do, if I'm going to use the ratio test, is we're going to start by taking the limit as n approaches infinity of a sub n plus 1. So this becomes 2 raised to the n plus 1 all over n plus 1 factorial, divided by a sub n, which is 2 to the n over n factorial. So this is my division. I probably should have had bigger absolute value signs here. So now when I clean this up, this becomes 2 to the n plus 1 times n factorial all over n plus 1 factorial times 2 to the n. And a lot of the time, I'm going to go straight to this step right here. I'm going to bypass this first step. I'm probably going to do that starting in the next example. So then let's look and see how this cleans up. Consider my 2 to the n plus 1 over 2 to the n. So remember, 2 to the n plus 1 is the same thing as 2 to the n times 2 to the 1. So therefore, you have a 2 to the n canceling out, and this right here would just leave me with 1, 2. And then think about the n factorial over the n plus 1 factorial. So n plus 1 factorial is just n plus 1 times n factorial. So your n factorials are canceling out, and all you're left with is an n plus 1. So this is equal to the limit as n approaches infinity of 2 over n plus 1. And when I take that limit, I get a 0. And 0 is less than 1. Therefore, the series converges absolutely by the ratio test. And remember, why do I know it converges absolutely? It's because if I add absolute value here, signs here, that series doesn't change at all. So therefore, it's going to converge absolutely. Let's take a look at the next example. So here, I guess I could have started with this. If I take absolute value signs here, the series doesn't change at all. So I know if I prove convergence, I'm proving absolutely convergent. Let's take the limit as n approaches infinity of a sub n plus 1. So this is n plus 1 squared. This becomes 3 to the n plus 2 all over 2 to the n plus 1. And then when I divide by a sub n, that's really multiplying by the reciprocal. So 2 to the n over n squared, 3 to the n plus 1. And let's think about what we can clean up. I know these 3's are going to clean up. I have 3 to the n plus 2 over 3 to the n plus 1. I could always consider the rules of exponents. So this is 3 to the n plus 2 minus n plus 1. So you see the n's canceling, and you're just left with 3 to the 2 minus 1, which is just a 3 to the first. So these are canceling and leaving me with just a 3 in the numerator. The 2's, same thing. If I have a 2 to the n over 2 to the n plus 1, well, that would leave me with just a 2 in the denominator. And then the n plus 1 squared over the n squared, I can't cancel anything here. So I would just have those hanging out. So I have the limit as n approaches infinity of a 3 and a 2, and then n plus 1 squared, n squared. And now when I consider that the dominating powers in both the numerator and the denominator are that quadratic leading term, I would just have the limit be the leading coefficients. So I'd have a 3 over a 2. And 3 over 2 is greater than 1. Therefore, my series is going to diverge. By the ratio test. Notice that it's not absolutely divergent. That's not a thing. This would only prove absolute convergence, but not absolute divergence. It's just divergent. And again, just reviewing the conclusions up here, less than 1 is converges, greater than 1 diverges, and equal 1 is inconclusive. Choose another test. All right, let's take a look at part C. So first, if I were to take the absolute value here, nothing would change. So therefore, if this thing is going to converge, I actually know it's going to absolutely converge. So let's take the limit as n approaches infinity of a sub n plus 1. So this becomes n plus 2 factorial over 3 to the n. When I divide by a sub n, that's multiplying by the reciprocal. All right, and so now let's, hope you guys caught that. So it should be n 3 to the n plus 1 up there. All right, so let's clean this up. Let's clean up the 3's first. If I take 3 to the n over 3 to the n plus 1, I'm going to be left with just 1 3 in that denominator. And then n plus 2 factorial is the same thing as n plus 2 times n plus 1 factorial. So these n plus 1 factorials would cancel, and I would have the limit as n approaches infinity of an n plus 2 over a 3 left. That's all that would be remaining. And that limit is equal to infinity, definitely greater than 0. Therefore, the series will diverge by the ratio test, because it's just going to be a very big number. So that's good to know. Let's add this to our conclusions up here, but I don't think it's explicitly up here. If it's greater than 1, and let's say or equals infinity, it's going to diverge. All right, so there's the ratio test. It's one of my favorites. I feel like it's really quick and easy, and I like that the absolute values are built in a lot of the time, so you can prove absolute convergence, which proves regular convergence. If you wanted to go back to this example right here, we proved it converges absolutely, and let's just remember that means it is also convergent, just plain old convergent. Because absolute convergence implies regular convergence. All right, and the last test is going to be the root test. And the reason I put these together is because their conclusions are the same. So if you have a series from n equals 1 to infinity of a to the n, it converges if the limit as n approaches infinity of the nth root of the absolute value of a sub n is less than 1. So again, if that limit is less than 1, it converges. If the limit is greater than 1, it diverges. And it's going to be inconclusive if the limit is equal to 1. So since you're taking the nth root, this is especially going to be a useful test if you have an entire rule a sub n raised to the nth power, because that nth root is going to cancel it out. And it's usually really easy to spot when this nth term test is going to be your game, not nth term test, why did I say that? When your root test is going to be your game plan. All right, so let's look here at this example. So I'm noticing right away that you have this 2 to the nth power and this n to the nth power. So I'm thinking I could rewrite this to see that you have e squared over n raised to the nth power. And when I see that nth power right here, that's when I'm thinking I'm going to try a root test. So the root test says I'm going to take the limit as n approaches infinity of the nth root of the absolute value of a sub n. And when you do that, you see this nth root and this nth power are going to cancel. So now I have the limit as n approaches infinity of e squared over n, the absolute value of e squared over n. But that's always going to be positive anyways. And now as n goes to infinity, I can see e squared is just a constant, so therefore the limit is 0. Therefore, the series is absolutely convergent. And thus, it's also convergent. If you wanted to go back and add these absolute value signs here, that's why I was able to add that absolute convergent, because e to the 2n over n to the nth is always going to be positive. So those absolute values don't do anything. Let's take a look at another example. So here you can see that you have 3n plus 4 over 2n all raised to the nth power. So I'm thinking I'm going to be using the root test. And I could go ahead now and notice if I take the absolute value signs here, this is always going to be positive from 1 to infinity. So if I prove convergence here, then it will be absolutely convergent. All right, so we're taking the limit as n approaches infinity of the nth root of the absolute value of 3n plus 4 over 2n all to the nth power. You have your nth root and your nth power canceling out. And this is going to be the limit as n approaches infinity of 3n plus 4 all over 2n here in absolute values. And then that limit is just going to be 3/2. And 3/2 is greater than 1. Therefore, the series will diverge by the root test. And I don't think I said the name over here, but I should over here make sure I add by the root test. It's always important that we name the test we used. So there's your 2 examples for the root test. You had 3 examples up above by the ratio test. Let's go back and make sure that, yes, I said by ratio test every time. And that is the end. You now have all of your tests for convergence and divergence. And that's all this week was about. This week is just about knowing what those tests are. We're going to work on putting those pieces together next week. I'm really proud of you guys. I know that this is a lot to go through. So I'm really proud of you. Congratulations. We're going to start putting all of these pieces together next week.